inspired by originally something is noticed from long back, something like Keshav study. Keshav not like basically Jalim study. So Jalim was saying that the height of radial distribution function, let's go to radial distribution function. So basically this middle graph, the middle graph second peak, basically it's a constantly increasing. So there was a wide belief that there is no connection to structure and dynamics of the system. The problem with glass systems, the more complexity arises because of the following reason. The glass, it's even this model is very simple model. It has two kind of particles. This is Cobb-Anderson model. So you have A and B particles. So now, relatively, your GR can represent most of the structures. So that is the idea. But if you have, let's say, you have some NiO01 or something like, or some oxygen, something, it's a very complicated compound. Very complicated compound. So in this case, GR is not simple like this. GR will have a very multiple peaks belong to various interparticle separations, something like some nickel IO, NiO3 or something, some compound is there. Oxygen, three type of oxygens, and these oxygen all will be connected to nickel and something. Then SiO2, something like again also three. Water itself H2O, so like all will have different separations. So it's not a very universal. Only thing that we need to find out in time to time what will be the right representation of local structures. Something like, okay, so now the question is whether people can find some connection between the relaxation time divergence from with the change in the structure. So this is basically the original idea. In a particular temperature, if you at a particular density, if you reduce the temperature, this system will shift to the right. Okay, so that you can explain, right? You can explain to the right why it should be. So the simple idea is that you have a Lennard-Jones potential is an asymmetric potential. So in an asymmetric potential, what happens is that if you want to close by, okay, closer by, so then that means actually then you know you are encountering the 12 part of the 1 by 12 part of the potential. So that is too steep. So the other side of the potential, okay, so the other type of the potential is basically soft. So that means you can go larger in that side. Okay. So now the kinetic energy is become unavailable. So then kinetic energy is basically that is what going to be converted into potential energy, because in a typical cycle, particle come closer and go away. So that is the structure. Force will come. So kinetic energy is unavailable. They cannot climb one side. So they will climb only the possibility is that you get to accumulate towards the other side. So that is what basically you are saying. Basically, you have the peak. Peak is shifting to right. Right is basically where the softer part is there, and they get peaked up. There is a minima, and around that minima, it is peaking up. So it is unable to climb this side, and belong to three potentials. One potential is basically the BB, AB, and then AA interaction. A is the strongest. BB is actually weakest. The first peak belong to BB. Even they all will have identical behavior because of this one. Actually, we can have some structures, something like here above. I can see that, yeah, so this is basically the structure. So you will have a particle. In this case, some A's and some B's are pictured directly, and then getting some mean ready. In fact, you cannot picture a Cobb-Anderson model in this way, because actually there will be two radiuses. So that means one particle don't have any hard sphere radius, because they keep one radius with A and B is different. B and B is again different, and actually everything depending on which pair it is, they are different. They are not actually mean. They are by definition their changes. So now this is just by averaging. So it is just taking the coordinate of one of the central coordinate and just plot it like that. So now in order to view it, we can actually project it in 2D. Basically 2D. Then there are some circles in that. In the circle, if you look at here, the circle here, you see that this is actually where the peak arises. So this blue line, you can actually call this blue line is basically belong to this R star, and we can call the density at this peak will be just R star.
The local density.
Yeah, there's a local density. So now there are, okay, so now the idea is that there are a lot of study on cages. Cage, actually what density. The cages have many definitions. Some of them are dynamical, some of them are static. Dynamical definition means the time required for the cage to break it. Basically, then there is no structural strong. Actually, people find out there are studies by Walter Kopp with some experimentalists on colloids. They say that there is a density fluctuation, that high density regions are forming. So there is a reason for to believe that this is what the high density region. One of the reasons why these pictures are misleading. All these diagrams are misleading in the sense that the particle does not stand there like idle. There is no idle. So basically everything is oscillating. This is a snapshot of the total oscillations. They are continuously oscillating. That means it's actually not there. In fact, some of them are in the peak of the kinetic energy, some of the peak of the potential energy. So they are at different states in every point. Every point they are actually either in this, they will completely convert into kinetic energy potential. This cycle is going on. So they are in somewhere there. But the only thing that when at high temperature, if you see the same shell, that will be different from low temperature. High temperature, this shell means that particle will be the particle will be easily move away from each other. They collectively move. There are a lot of kinetic energy is available. So every possible moves are possible. So that means actually they don't see each other in a same instant of time. You take a snapshot and some of them are, after some time this particle may not be even near to that particle in case of high kinetic energy. But if there is a low kinetic energy, then most of the time it will be like a stable. So that's a quasi-stable structure of the shell, quasi-stable structure. So now that actually there is no clear idea behind how a cage resulting in slow relaxation. We can understand it because actually if something is going outward very fast at high temperature, so the idea is that they will go very far and then it will even pushing many particles because kinetic energy is in abundant, so they will move in collectively. So even moves will be same in low temperature and high temperature everywhere. So that we can see here. So now coming back to too much of expansion. So actually this is where we have calculated some strings. It is not the string of mobile particles. The old systems, all the strings in the system. So it doesn't even distinguish A and B. So the sole purpose is that in this work, what we are trying to do is like the title suggests, connection between paths of string like motion, free volume in molecular cages. Okay, so this is what basically our try. So we have a theory which is basically coming back to the free volume theory that is belong to molecular cages, and there will be connection between paths of string like motions. So now these are the two things we wanted to connect in this work. Okay, so we'll see that there again many attempts. This is one of the attempts to do that. So let's do that. This is actually one of the uniqueness of this attempt is that this is actually belong to a structural. We are trying to get a structure and then connect the structure to
dynamics.
To dynamics. So earlier actually people were trying that local motion to global motion. If you know, maybe you can see that even Chandan Das Gupta and something, they have calculated that beta relaxation how is connected to alpha relaxation. So typically this structure is actually the time of beta. Beta means short time. So within the cage. Alpha means when the system will actually break the cage and move away from it. Okay, so how that belongs. So now the thing we have this picture. So the picture, the first is basically P0. This is an all particle string. So if you look at the blue, that is basically 3 at temperature 3. So it is more or less straight line. So the thing is that it is actually orderly. That means actually again, this is a all particle. That means it is not mobile particles. So since it is not mobile particles, all the particles not moving like a string will be P0. Will be P0, the first value. Achha. One particle, that is a single particle motion. That will be majority. So that will be like a few will P1. Move. P1. Yeah, P1. Yeah, not P0. P1. Yeah, basically P1. Yeah, P1. So basically P1, first one particle motion. So the one is one particle. That's why it is huge dip. That is because it is actually the old particle, not the mobile species. Okay. So now the thing is that in that high temperature, most of them are mobile. So you can see that blue. will be following exponentially relaxing path. It was actually semi-log plot, it's giving straight line. But again, the moment straight line will go away, the moment we actually come down and to the other graphs will be having basically most of the particle will be, there are many strings because there are one idea here, it's a cobalancing model. B particle is strongly attracted to A particle. So that means the best possibility of a string is basically AB string. So if you put A alone string, that is basically even against natural relaxation process. So now if you look at the first particle, actually there is a huge dip. So now what happens is as the temperature reduces, string-like motion become lengthier. So we will see that the first blue will actually crossing the tail part actually crossing over to longer scale. So that means like longer length. So that means that longer strings are possible at lower temperature. So the probability of getting longer string become reduces at high temperature very fast. So the string may have a crossing effect. So we'll see the what is crossing effect here. What we call it as crossing here. Here the green lines is a typical string like path. So where they displace each other, yes. I'm good, do it. But there might crossing. You'll have another crossing. So the two green lines, which is basically crossing each other. So that means before completing one motion, others can cross it. So there can be multiple crossings. So if kinetic energy is high, the crossings become very large. So that means they don't really form like a string, but then actually by the time they will cross, and actually even in a dense environment, this is the possible way of doing it. So actually that is a structural requirement of the system that relaxation should be in a dense environment should have strictly in kind of like a multiple arrows crossing. So the string-like motion is actually natural pathway of that. But how much string will occur, that depending on available kinetic energy.
Okay.
So how much will string will take place? So then now we just put P1 alone in all densities, temperatures, etc. You'll see that when the 1.8 density, that's very high density, in that density you'll see that everything is very straight. So that means actually it's uniformly decreases with temperature. This is 1 by T. So if you go this side, it actually decreases. Again, string-like motion actually decreases with temperature. So temperature high, string length actually increases, but string-like motion actually decreases. Okay. Because there's no kinetic energy there. In addition to even that is representation is that if you look at black and black and red one is WC model and black is basically cobalancing. So that means if you look at 1.8, you will see that at a given the resistance to the path become larger in the cobalancing. That is because of the attractive part. So there is attraction. So that resistance means basically the friction. Particle move along a string line, the friction will go large. Friction. So the friction will be high in by default. You can think that because friction means the amount of energy transferred to other particle. That's very simple. So if you have a string and it is through an attractive channel it travels, it will actually transfer more outside. So that means the string length will be smaller in that sense. If you look at here, then you will see that red actually is lower, black is higher. Black is higher means it's actually the single particle motion. So black has higher single particle motions. So that means basically the strings always form some resistance there. That's the message. In addition to that, if you look at lowest density, there is 1.2. 1.2 density basically triangles. This side you have dispersed triangles. You'll see that at high temperature, majority there is no particle order. You'll see that order goes away at WC model. So that is because actually you are lower density. There's no constraining potentials. So the strings become more loose and kinetic energy become more available. So I think this graph is more or less that's what. So the basic idea is that now this message from this graph is that so you have string-like motion that actually increases length increases by temperature decreases. Okay, and also there is actually the singlet motions are majority at lower temperature. If you look at 80% of them, if you look at the top part, 80% have no connection. unconnected motions. So the okay. So now okay. So now we are actually planning to find out the connection between original relaxation time and the string-like motions, and through making a microscopic model. So now this now if you look at the okay, now in order to do this one way we can simply one simple microscopic model is basically free volume theory. If anybody look into free volume theories of actual theory, so the basically from conservation laws, so they will actually have a total volume available to the system is there. So that is in a particular manner total volume is there. So actually if every particle, if it's a hard sphere, then you can actually have a exact sum of the volume will be total volume, otherwise hard sphere means remaining volume belong to hard spheres. So in that conservation law you can have a statistical mechanics of the problem directly. Then you can have a rate probability of finding something, a volume, and then for inverse of that probability you will get the rate at which transition takes place. So from that rate theory you can have an exponential relaxation. So that is actually the hard sphere theory of basically by the original free volume theory. I forgot the scientist name. Actually I'll have to Doolittle. Yeah, I think Doolittle. And I think that is his name. So now, yeah, so that is the original hard sphere theory of Doolittle. Okay, so now the thing is that is a statistical theory, that is a microscopic theory. But again, the problem with that, this hard sphere is actually an approximation. Soft potentials, I don't know how much they will close around it. In addition, like that theory also have some approximation. The idea is that if you have a packing of spheres, okay, so the packing of spheres have extra free space always. There should, if we look at here, okay, see, there will be always extra free space. Even if you press the hard sphere, they don't close. So there will be voids which is permanently also inaccessible. It is not only that volume, but there's a permanently inaccessible volumes are there when spheres come closer. So now the thing is that how much of this permanently inaccessible volume come into picture? That's the question. So now, so in order to model these ideas, what we can do is that you look at the type of channels, what happens to these channels. So this is basically the GR belong to a channel. The peak of GR belongs to channel. So how do you look at it? Yeah, so if you look at here, okay, so I'll do it here. This is a channel. This is a channel of relaxation. Okay, so in this channel, so the idea is that free volume is basically the along a line how much volume is available. It is not actually the total. Along this volume, how much space is available between them. Okay. So if the space is available along this channel, it will go. So you don't really worry about the total volume, free volume available, but actually along one particular channel, how much it is possible, how much free volume is available. That is, this channel we can actually model because you will see that this peak belong to this distance, right? This distance. Yeah. So that means this is basically, if you look at here the particle as reference, this is actually where the next particle. So from that you should get a measure of the free volume available in the system. If you stand here on B, and how much particles are accumulated at A. So this is basically, now one more thing, if you look at one particle here, let's say A. So see the channel this green line along B, this is actually surrounding A. So we can call these particles are actually caging particles. So these particles actually cage A, and B is actually is a along a path. So now every particle is caged by the string-like paths surrounding it. Okay. So that is the argument. So the cage has no structural analog as such. See, the cage, we don't know how exactly a cage participates in the relaxation motion. Okay, so now if you look at any particle surrounding that, there is a relaxation path, which is string-like relaxation paths, and most of them are not engaged. That's the question. So we don't engaged means actually if you look at this graph. So if you look at here, okay, So actually, if 80 percentage is actually not because 80 percentage, so it's a these are a high low temperature values, right? These are low temperature values. So at low temperature, 80 percentage of that is not engaged at all. So you are not worried about how long this will go, but we are worried about how like how the pushing starts between only over two pairs. We don't take it actually, otherwise we need to, if we want to have an exact calculation, then we need to find out how many of the paths. So there might be crossing paths means even at low temperature one particle try to move in this way, another particle will be moving this way, so there might be crossing paths. So that if that will not lead to a string like motion, but actually there that lead to a pushing motions which is slowly relaxing. So majority of the particles are slowly relaxing through the multiple pushes. So the thing is that long again string actually become weakens, string like motions weakens, and this pushing path is actually modeled from the free body. So that is what we are trying. So now the thing is again string like this is a condition from this one. So
As it relaxes further and further, the string-like motion become weakens.
yeah, string like weakens, but that is the only major way of doing it. But again everything become other one belong to the slow motion. And actual relaxation is belong to slow motion only, not the strings. Strings actually perturb. So actually ideal way, if we can find out account for both separately, then we can actually find out if we can then exact dynamics, because they belong to two category of motions. One category is slow, the another is actually the fast. Fast is basically string, slow is basically this push, multiple push. So now we are looking at multiple pushes. So now if you look at this channel here, so the idea is that this also take one thing what literature of the super cold, especially models like Kobayashi, always find that there are specific structures form as the temperature reduces. Not one icos like this icosphere or not. There are actually there are studies by that what is this group? So they have a Steinhardt is the oldest one.
The QLM parameter.
Yeah, QLM parameter. But Steinhardt not like somebody who is
Glotzer?
Kozlovich actually studies actually. There's a specific British group, and his name is Dyer not. Again.
Glotzer.
Okay.
Tanaka. No.
Tanaka is not English.
There are two. Okay, so
Doneba.
okay, so
Donati.
Russo. No. John Russo.
English.
Rosso and Tanaka as a collaborator, so they always work together. So they have a program that again like some software for identifying these structures in their website. I might have told even before. Okay, again name issue is there. Kozlovich has near to that, so they have a collaboration paper, but not this person. This person actually identified various structures, but again they have different. All the ideas they have different structures. So actually these are not spherical like structures. Basically they get compacted in a different manner as temperature reduces. So the peak position belong to one structure. They get compacted as the temperature reduces. Then after that they switch to another structure and they get compacted in that structure. So different structures have different compacting parameters. So the one of the reason why the structure is not smooth variation. Structural variations with decrease of temperature is actually different, belong to different actually bands. Say they one band.
Okay.
They belong to one band. So towards the end of the band, so basically this is actually the high value means low temperature.
This is a position of peak.
Yeah, position of peak. They actually have a different structure. That structure get cooled down. At some point, they have to change to new structure to get that is a new minimum.
Okay.
So they belong to new minima.
Okay.
So that is basically the non-uniform compaction.
Okay.
So that means. So now because of non-uniform compaction, it is actually this contain the volume. So now let's say raw local. So you can actually show that. Okay, let's the structure theory goes like this. We have a simple theory for that. We have this GR at star, we call it raw local. Okay, so rho local is basically, if you look at here, this is the rho local. Along this circle there is a rho local. So this is a rho local. So the rho local is at gr star at r star. Okay, so now this free volume is proportional to like Vm inverse. That is a theory by some studies earlier. So we adapt their idea.
Okay.
That is this is theory on polymer dynamics. So since they polymers, they actually look at these are connected particles. Here in the strings are also connected particles. Okay, connected means in a virtually connected, not really by a bond. So now E is proportional to Vm inverse, and then we can actually, the volume in a channel is proportional to number of particles there divided by the rho minus rho local. So rho minus rho zero is rho local is basically that this is excess free volume. So that means number of particles divided by rho zero is actually the maximum you can actually pack it, and then how much excess currently it has. So this gives some number free volume. Okay, so now if you look at here, this V is actually here, and then the original free volume formula reads like this: B V0 by V minus V0, and V is nearly equal to 1. Now it's replaced by this formula. V is replaced by this one, and rho 0 is actually the higher density. You don't have to substitute anything there, basically. So now if you substitute here, because if this is substitute in the below, then actually they make it entire thing inverse. So now this can be written in this form: B rho local by rho 0 rho local. Okay, so once you substitute that, and then you get the formula, and this is actually, now we test it against actual simulations. When you do simulations and then if we fit it, it will get to straight line fit. So now if you look at straight line fit, only one thing that you know, that the structure actually, structural inhomogeneity is already accounted here, because it actually does not follow in the straight line, but in fact it goes down, up, down, up, down, up. So basically the peak height also varies and peak width also varies. No, uniformly, because actually the GR peak position actually same for some kind of variations. After that it just flips, it go to another structure. So now the thing is that will change the density fluctuations in the channel itself, not uniformly. So that you can see here. This actually go down, then up, then down, but it doesn't go away from that. It actually go up, again it falls. So then actually it's a like fluctuating line. So but actually it's on average it falls on that. But on the other hand, if you look at temperature dependency, that is uniform. So that means there will be a connection between these two graphs, which are identical in structure. So that means there is a reference temperature below which system cannot go. That is basically divergence temperature, and there is a divergent structure. So now equate both of them, you can get a structure connection between rho local connected from temperature. And then this formula is again tested against a simulation. So basically you have simulation there, and on the simulation data you just use this formula to plot it. So now when you plot it, you will see that initially at high temperature they don't fall. It's they start falling after some time. This line, black line, this is here, but actually this black line fall on the last point. This is actually for the 1.2. And if you look at this WCA model, have only few very little supercooled there, so it will be true only at the last points, not early points. It's a huge deviations. If you look at that, become even at 1.4 again. Actually, towards the end they match. The formula matches. Here also towards the end they matches, and here it's actually again string is very much strongly connected in 1.8, because that is a very high density. So that means actually the deviation become weaker, but again at the end they matches. So this is what the total idea behind that paper.
Okay.
So yeah, I will try to convey these ideas more coherent manner and trying to make it one basic writing I have done. So I'll just keep looking at something more coherent I can make it, or even fluctuations. So this is what basically the graph is all about. Okay. Okay. So I'll try to get refine bit more on that.